In the last section, we dealt with angle and perpendicular bisectors. Section 5.3 looks at how those two things work inside of triangles. Some vocabulary before we start on the good stuff. When three or more lines intersect at a single point, those lines are said to be concurrent. It looks like these lines here. Pretty simple, right? Lots of lines, they all meet at a single point. The point where the concurrent lines meet is known as the point of concurrency. That's this point here. Again, not too bad, right? Next vocabulary word is circumscribed. A circle is circumscribed about a polygon when each vertex of the polygon lies in the circle. In this usage, about means around. So we are talking about a circle that is around a polygon. It helps to see some examples. Here is a lovely red triangle. This is what the circumscribed circle about this triangle looks like. Here we have a beautiful blue pentagon. This is the circumscribed circle about that pentagon. Finally, there is a lovely green hexagon. This is the circle circumscribed about it. You probably get the idea now. This is what it means for a circle to be circumscribed about a polygon. For the purposes of this lesson, though, we will only be focusing on circles circumscribed about a triangle. We will leave the others for another day. One interesting point, though, every triangle has a circumscribed circle. However, that is not true for any other polygon. Only triangles are guaranteed to have a circumscribed circle. So all that vocabulary was to get us to this point. In every triangle, the perpendicular bisectors are concurrent. Let's draw them in for this triangle below. You can see that, yes, the perpendicular bisectors really are concurrent for this triangle. The point of concurrency of the perpendicular bisectors of a triangle is known as the circumcenter. So that's this point here. The circumcenter has a special property. It is equidistant from all three vertices of the triangle. So all three of these dashed blue line segments are the same length. Can you think of anything you might be able to do with a point that is equidistant from the vertices? What if all those dashed blue line segments were radii? You could draw a circle. That circle is the circumscribed circle for our triangle. In fact, the reason it is even called the circumcenter is because it is the circumscribed circle's center. You'll end up constructing circumscribed circles. So you'll need to construct the perpendicular bisectors to find the circumcenter, then use the circumcenter to draw your circumscribed circle. Sound fun? Last thing about the circumcenter. In this example, I have worked with an acute triangle. With an acute triangle, the circumcenter always ends up inside of the triangle. However, if I work with a right triangle, the circumcenter ends up on the edge of the triangle. It happens to be the midpoint of the hypotenuse, too. If you were to draw in the circumscribed circle with this one, it would look like this. That hypotenuse of the right triangle ends up as a diameter of the circumscribed circle. But if I work with an obtuse triangle, the circumcenter ends up on the outside of the triangle. Students really don't like that sometimes. They really think it should be inside. But if I draw in the perpendicular bisectors, you can see that they do, in fact, meet outside of the triangle, and the circumscribed circle would look like this. So I know it won't sit well with some of you that the point of concurrency is outside of the triangle, but you'll just have to get used to it. Now we deal with inscribed instead of circumscribed. A circle is inscribed in a polygon if the edge of the circle touches each side of the polygon in exactly one spot. It will make more sense if you see some examples. Inscribed and in should have pointed you in the direction that we are talking about a circle on the inside of the polygon instead of the outside this time. Technically, the definition of inscribed should use the vocabulary word tangent in it, but we won't cover tangent for a while yet. Hopefully those pictures give you a good idea of what it means for a circle to be inscribed in a polygon. Just like the circumscribed circles, for this section we will only be focusing on the triangles. We will deal with the other polygons at a later date. And also like the circumscribed circles, only triangles are guaranteed to always have an inscribed circle. None of the other polygons will always have an inscribed circle. In every triangle, the angle bisectors are concurrent. Let's draw them in for this triangle below. You can see that yes, the angle bisectors really are concurrent for this triangle. The point of concurrency of the angle bisectors of a triangle is known as the incenter. So that's this point here. The incenter has a special property. It is equidistant from all three sides of the triangle. So all three of these dashed blue line segments are the same length. Notice the 90-degree marks to show we are talking about the shortest distance to the line. Can you think of anything you might be able to do with a point that is equidistant from the sides? What if all those dashed blue line segments were radii? You could draw a circle. That circle is the inscribed circle for our triangle. In fact, the reason it is even called the incenter is because it is the inscribed circle's center. You will end up constructing inscribed circles. So you'll need to construct the angle bisectors to find the incenter, then construct one of the radii, then draw the circle from the center. Then draw the circle from your incenter. Sound fun? Last thing before we close the book on this section. Unlike the circumcenter, the incenter of a triangle is always on the inside of the triangle. That will make some of you very happy.